Alright, we're going to take a look at two last problems here in terms of our equations that we've been solving. And then we'll take one last look at a practical application for some of this. So, one more equation that's going to look like this. We're going to do 2 log base 5 of 3x equals 4. And again, back to basic algebra, at least until we can get as far as we can, until we have to use some of our properties or our logarithms. So we're just going to take this, divide this whole side by 2, this whole side by 2, so that reduces. So we get log base 5 of 3x equals 2. And right now, I'm going right to the circle. So again, I'm going to do 5 raised to the second equals 3x. And obviously 5 to the second is 25, and that equals 3x. Divide by 3 on both sides, and I'm going to end up getting x equals 25/3. Now, we talked about checking these problems. Might not be so easy here unless you did a little bit of extra work up here with change of base and so on. So for the most part, make sure that everything's going to work for you. The big thing that I would probably check for the time being would be this 25/3 when you plug it into the original equation up here, where we had 2 log 5 and then 3 times 25/3 equals 4. This simplifies, so we get 2 log base 5 of 25, and the first thing we want to check is, does this give us a positive value? If it doesn't, we can't find the log of a negative, so that wouldn't be defined. So far so good. Now in this one, 5 to the second power does equal 25, so this part is 2 times the 2 that we had out front, and it does equal 4. So it does check out. I don't have to worry about change of base, I guess. I don't have to worry about trying to figure out what to do without a calculator. It works out pretty nicely. Alright, our last problem I want to look at in this section looks something like this. We're going to go with log of 5x, and we're going to add log of x minus 1, and we're going to set the left side all equal to 2. Now we're using common logarithms this time, so base 10 is back, and on this one I want to combine this to get a single logarithm, so we're going to go with addition being the same as multiplication when we do product rule. So we're going to turn this into a single logarithm of 5x times x minus 1. So just using product rule from product property. I can't talk. So I'm going to simplify the inside here just by doing a quick distribution. So I'm going to get 5x squared minus 5x, and that equals 2. Then I'm going to go with our circle again. So since this is base 10, we're going to do 10 raised to the second power equals that. So 10 to the second power is 100. That's going to equal 5x squared minus 5x. And again, since it looks like we're dealing with quadratic here, we're going to try and get everything on one side, set it equal to 0. So I'm just going to subtract the 100 over to the right side. And then we're going to simplify. So on this one, we have a common factor on the right side of 5, which leaves us with x squared minus x minus 20, and that breaks down pretty nice into x minus 5, x plus 4. So we need a little more room, so we're going to bring it back up top here. So if I do my factors, I've got 0 equals 5, which obviously is not true. I'm going to get 0 equals x minus 5, and we're going to get 0 equals Oops, and I miswrote that. That should be x plus 4. 0 equals x plus 4. So I'm going to add 5 to this side. So 5 equals x. I'm going to subtract 4 from both sides. Negative 4 equals x. And those are my two possible solutions. Now we're going to go and check them again. So if I put 5 over here, I'm going to get log of 25 plus, put 5 here, 5 minus 1 is 4, so log of 4, that all equals 2, at least we're hoping it's going to equal 2. And we'll actually make a 2 look like a 2. Now again, I can put these together with addition and do product rule, which just says I can turn it into a single log of 25 times 4, which is 100. And then again, because this is base 10, 10 to the second power equals 100, so I do get 2 equals 2. So we're good there. To check the second one out, we would get log 5 times negative 4 is negative 20. And I can stop without doing anything else because, remember, our logarithms that we're solving for have to be greater than 0 or positive. So that one's out, which means that's an extraneous rut. So in this case, we only had one solution out of the two possible answers that we thought we found. So again, check your work. Don't just accept your answer and say that it's good enough. So, all right, let's go on to one last problem here in this section. And again, we're going to make it an application problem. And for this application problem, we're going to take a look at something known as doubling time. And this will be a type of problem that we'll use a couple different situations throughout the rest of the course. So we're going to look at doubling investment in this particular one. Now again, like I said, we're going to use this in some more form. So in general, we're just going to call this doubling time. In other words, when is everything going to be double when it started? Alright, so here's our situation for this particular problem. We're going to deposit $500. And we're going to deposit that at 6 3/4%. Now the other thing is, we've already dealt with this before, but we're going to talk about this being compounded continuously. And again, not very realistic, but it lends itself to solving this type of a problem. And again, everyone seems to understand money, so it's a good application for this one. So we've talked about our PERT and QUIRT problems. So since it's continuously is our key here, we're going to set this one up in a form like this. Our final amount is going to be our principal times E raised to the rate times time. So if we start this one out, our principal amount was $500. Our rate, remember we have to write this as a decimal, so 0.00675 times our time, which we don't know. And that's what we want to find out. We want to know how long it's going to take for our investment to double. Well, if we start with a 500 to make that double, obviously we're going to end up with $1,000. So we'll leave everything on the right side, put that 1,000 over on the left, and we end up with this. Alright, again, looks a little involved, but not really. Again, since the t is what we want to solve, and the t is involved as an exponent with the e, we got to get rid of this 500. So pretty simple. We just divide both sides by 500, so we're back to isolating. Cancels on the right side, left side turns into a 2. Now it doesn't look nearly as intimidating as what it maybe started out to early on in the problem. So now we got that. Now again, we've worked with some of these problems before. Since this is a base e, I want to do a natural log. So I'm going to do natural log of 2 and natural log of all of this on the right side. Now on the left side, not much I can do with that other than say natural log of 2 again. On the right side, again, because this is base e, our bases match, the exponent is our solution to the right side. So we get 0.00675 t. Alright, again, I'm going to move this up so we have a little more room to work with and just recopy it. So no math happening here, just cleaning up the place a little bit. And again, mathematically, I want to isolate t. I'm just going to divide. So again, very basic math. We're going to do that on both sides. And again, my technology is kind of failing me here. So we want to make sure this actually turns out to look somewhat nice over here. 5 times t. So on this side, everything cancels except t, which is what we wanted because we're looking for the time it took to double. And on this side, we're just going to go to the calculator and do natural log of 2 divided by, not the t, but 0.00675. And obviously we're not going to get a nice number here, so let's do a little rounding. And we'll go to 3 decimal places on this one. And, oops, I guess I did my work to 2 decimal places. And when we did this one, it comes out to be about 10.27 on the calculator. So a little more than 10 years. So we'll just say 10 plus years to double. Sometime after 10 years. Now one thing that turns out really nice about this, and it's something like I said we'll run into a little bit later as well, what's going to happen is we can do this every single time, and whatever we start with, if we double it, once we do this step right here where we divide, we're always going to get 2, we're always going to do a natural log, and pretty soon we end up with natural log of 2 divided by whatever the rate was equals our time. And that's eventually going to be used in a lot of situations as our doubling formula. So again, this is the method to find it. Eventually it breaks down into a shortcut. So that's section 3.4.